Well, happy Friday, January the 29th. It's hard to believe that when you come back to school on Monday, it's going to be February already. Time is just slipping into the future, okay? But we're still pretty much on track to be finished with what we need to be doing on time, but we got to just keep pressing forward. So today we're going to talk about measuring the rate of reactions. Yesterday we talked about all the different factors that affected the rate, what was necessary for the reaction to actually occur, an effective collision. Now we want to go with measuring the rate of a reaction. Okay? So the rate is always going to be measured by the change in concentration divided by the change in time. The change in concentration. Now, most of the time you just pick one of the reactants. We can have the rate is going to equal the change in concentration of a reactant, which is going to be negative because the concentration is going to be going down. Or we can have the rate of the formation of a product, which is going to be positive because its concentration is going up. When we look at that graphically, it's always going to look like this. It's never going to be a linear line. Well, I guess is that redundant? It's never going to be linear. Okay? It's always going to be this kind of logarithmic curve. Why does the rate slow down? Based upon what we just talked about, why does the rate slow down as the reaction proceeds? As the reaction continues to go here, there's less and less of this, meaning what? In terms of what we just talked about.
There's less collisions.
Less collisions. So the collisions begin to get fewer and fewer and fewer. You're not really changing the energy. We're assuming everything's happening at constant temperature, but we're having fewer and fewer reactants, and so the reaction is slowing down. Most of the time we'll be talking about measuring the initial rate. What's the rate when it first starts? Okay? So we can get an average rate, okay, just by going for how much, where did we start, where did we end, what's the time, just like that. But what we really want to do is find out what's the instantaneous rate. The instantaneous rate, what do you think that is?
The reaction time.
It is going to be that over time, but just by definition, what would be the instantaneous rate? Don't make it complicated. Okay? So they're pointing to this point right here. They're getting the instantaneous rate. What is that? Not even mathematically, just by definition, what would that mean? You're making this way harder than it is.
First rate.
It's the first rate. It's the rate at that moment. That instant. It's the instantaneous rate, the rate at that instant. If I want to get the rate at this point, that's the instantaneous rate at time 600 seconds. At any particular instant. Now the way that you're going to do that, to get the instantaneous rate, the rate at any time t, okay? And it's going to be equal to the slope of the tangent line to the graph at that time. Now you're never going to have to calculate that, but you're going to need to know how to calculate it. You need to know that, so right here, notice again, and getting the tangent, any y'all in calculus? Like first derivative, right?
Yeah.
Okay, so this is all calculus based. Okay, now we don't have to know the calculus to do that, but I'm just trying to relate it, make it real for you. Okay, but it's the tangent, the first derivative of my line function, the tangent at that particular point t. So notice here, the initial rate, the slope of this line, that's that dotted line is the slope, the tangent, is going to be steeper than the tangent line right here at this point. Okay? Now, the reason why you're never going to have to do that is because it's very difficult to eyeball an exact tangent line. Okay? You know, so to try to calculate this, now if you have your fancy calculators, you could plug it into your fancy calculator and get the slope of the tangent at doing that. But you're never going to be required to do that. You just need to be able to know, looking at a graph like this, that that's how you get it. The average is obviously, the average you pick a time initial, time final, get the change in concentration over that time, that's your average rate. That really doesn't do us much good because it changes so much throughout the reaction. But again, when you're looking at a reaction rate, it's never going to be, the slope is never going to be straight, it's never going to be linear. It's always going to have this kind of a curve. It's always going to slow down as the reaction proceeds because there's fewer collisions. Okay? So we need to be able to look at the graph and be able to understand the instantaneous rate. Be able to get that. All right, so that's basics number one. Where is the actual equation? Here it is. Okay, so now if you're curious, I'm on page 580 in the textbook. Okay, so we're zooming through. We're on page 580. We've already done chapter 19, which is farther on down. So just to kind of give you a preview, we have chapter 14 left, this one. 15 is equilibrium. This is going to be like a 2-week unit. Equilibrium will be like a two-week unit. Then we're going to do chapter 20, which is electrochemistry, a 2-week unit. That's 6 weeks. Then we're going to use the rest of the time to do chapter 16 and the half of 17, which is acids and bases. Then we're done. Okay? So we can see a light at the end of the tunnel. We just always pray it's not that oncoming train. Okay? That really is hope. So if I look at here, okay? Equation, likewise, the stoichiometry equation 14.3, which must be on a previous page, indicates that 1 mole of C4H something OH is produced for each mole of C4H9. So if I look at this equation, well, let's go back and just actually get it, 14.3. Okay, so here's my equation. C4H9Cl plus H2O goes to C4H9OH plus HCl. So when we want to write a rate law for this, if I want to write a rate law, I'm going to have to pick either the rate of disappearance of one of the reactants or the rate of formation of one of the products. So I can say that the rate of my reaction is going to equal the change in concentration of C4H9Cl over the change in time, but that's going to be negative because the change in concentration is going to be going down. It's going to be a negative. But that's also going to be the same. I could also say it's a negative change in concentration of the H2O over time, which is also going to be the same as the positive change in concentration of the C4H9OH over delta T, which is equal to the positive change in concentration of HCl over delta T. This is called the relative rate law. rates expressed in terms of the stoichiometry, your favorite word, of the reaction. Okay? Now, if I want to just look at another example of that, if I said, give me an example, we can even use this one. 2 O3s going to 3 O2s. Okay? I want to write the relative rate law. Which one is going to be, which one's concentration is going to change the most at any given point? Are they going to change at the same rate? Reagan's shaking her head no. Why?
Well, at the beginning it's like only ozone, and then near the end it's like only O2.
Okay? Here's the key word here, stoichiometry. Stoichiometry always deals with coefficients, right? 2 of these are going to be breaking down, but 3 of these are going to be forming. So this is going to be forming at 3/2 the speed of this one. Okay, just from stoichiometry, just for every 2 of these that break apart, 3 of these form. So obviously this is going to be forming faster than this is disappearing. So we're going to say the rate is equal to the negative change in concentration of O3 divided by, actually let me change that. We're going to do it this way. Negative 1/2 times the change in concentration of O3 over delta T is going to equal the positive 1/3 times the change in concentration of O2 over delta T. Okay? So when we're trying to compare the relative rates to one another, okay, this rate and this rate, okay, are going to be in this kind of ratio right here. And we always just take the coefficient and put it over 1, and it's going to make it work out. But it has to do with the fact that this is going to form 3 times faster than this one. If you were to look at the rate of O2, if you brought this 3, notice we multiply both sides by 3. So we would say that the rate of O2 is 3/2 the rate of O3. The rate of formation of O2 is 3/2 the rate of disappearance of this. So it gets you the same ratio as what we're just kind of talking about here, but you always just take whatever the coefficient is and you just put it 1 over that, and that gives you your relative rate, gives you the stoichiometric factors that give us the relative rate law. And it's all based upon the equation. So that's all just 2 right quick. If we go to the end of the chapter, I don't need glasses, I can't read. So if I look at, this is number 24 on page 619. So for each of the following gas phase reactions, write the rate expression in terms of the appearance of each product and the disappearance of each reactant. In other words, the relative rate laws. How do they compare to each other? Well, it's going to be pretty straightforward. All I'm gonna have to say, okay, so I have 2H2O going to 2H2 plus O2. So my rate, I'm gonna say, is equal to negative 1/2 the change in concentration of H2O divided by the change in time. It's gonna equal the positive 1/2 H2 over delta T is equal to just the change in concentration of O2 times over delta T. So in other words, the hydrogen, the water, let's try it back again. Hydrogen is going to be formed at the same rate at which the water is decomposing. It's 2 to 2. But the oxygen is going to be 1/2 that. Okay? 1/2 that. Now, it doesn't look like it's saying that, but it really is that the oxygen's rate is 1/2 the rate of the water's. When you look at that mathematically, oxygen's rate is going to be 1/2 the rate of the water's. It's going to be 1/2 the rate of the formation of the hydrogens. So you just put it 1 over, and that's how we write the relative rate law. But it's just, we can really kind of figure it out. If I knew the rate of this one was 10 molar per hour, well then what's the rate of formation of this one going to be? 5 molar per hour. Okay? So that's really the practical application of this, is just being able to do this. But this is putting it mathematically on how it works. Okay? Most of the time on the AP test, we're going to find that they'll give you, you know, the concentration of the rate of disappearance of one. They'll ask, well, what's the rate of formation of something else? And that's where it's just the stoichiometric coefficients. Okay? So what would, I mean, do I need to do any more of these? I mean, it's pretty straightforward, right? Rate is going to equal negative 1/2. The reactants are always negative. Why? Okay, you got to speak up a little bit louder than that.
They're reacting, so they're going down.
They're going down. They're being used up, so the concentration's decreasing, whereas products are increasing. Okay? So here's just, consider the combustion of hydrogen. Hydrogen plus oxygen makes water. If hydrogen is burning at the rate of 0.48 moles per second, what is the rate of consumption of oxygen? Here's my equation. Hydrogen's here plus oxygen goes to water. If a hydrogen's being consumed at 0.48 moles per second, what's the oxygen being consumed? 0.24, half of that. Right? Some of y'all are kind of, you know, I always say, staring at this like a cow stares at a new gate. Like, you know, when did that get there? So, what is the rate of formation of water vapor? Y'all should be all screaming this out at once because it's so intuitively obvious.
0.48.
0.48. 2 makes 2, so 0.48 is going to make 0.48. 2 combines with 1, so 0.48 is going to be reacting at 0.24. The coefficients, it's a stoichiometric relationship using the coefficients. Okay? So, when we come in on Monday, we're going to go in and start looking at how do I actually calculate the rate. Okay? Again, we're going to take the derivative of this rate law. We're going to have 2 different forms of the rate law. We're going to have the derivative form, the first derivative, and then we're going to have the integrated form. So we're going to be using the calculus. Now, I'm just going to tell you what those forms are, and it's going to be easy because you don't have to know the calculus. But it's nice if you're in calculus, you can see the application of why you're learning the math. And again, just more proof that math, calculus in and of itself is not its own subject. It's a tool that scientists have created to be able to do real problems. Okay? Newton didn't discover or invent calculus just because he liked math. He needed it to solve a physics problem. Okay? He just, and I don't know how you just create your own math to be able to solve a problem, but that's why he's in the science books and I'm not. All right, hope you all have a wonderful weekend. I do strongly encourage you. You don't have to admit necessarily that you read it or that you enjoyed it. You can say it was boring, but I really think that you will enjoy reading that little 8 to 9 page excerpt from that book. And I'm hoping it's going to whet your appetite to where you want to read the whole book. And so at one point I had 2 copies of it, but I think I lent one out and never got it back. But anyway, I just think that you'll find it interesting, especially if you have any interest in history at all. All right, have a wonderful day.
Go ahead and lift.